Part 23. Braids, links, and higher topological structures.
Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, the single cyclic movement from which all reality unfolds. When phi differentiates, that one movement generates its first derivatives, and with them, the three dimensions appear at once: time as omega, space as k, and motion as v. From that first differentiation upward, every higher derivative is an echo of the one below it, an infinite ascent of finer and finer reflections of phi's original movement. And because the dimensions are born from that first echo, time, space, and motion also reverberate into infinity, carrying phi's unfolding into ever deeper rhythms, structures, and flows. Thus, the entire universe, every law, every pattern, every force, every particle, every phenomenon, is nothing but phi, endlessly echoing through its derivatives and their dimensional shadows. All of existence is the infinite echo of one field. Today, we listen to just one of those echoes. We have already mapped the singular skeleton. In our last journey, we explored the sigma set, the points, lines, and surfaces where phi becomes singular, anchoring the digital topological charges to specific locations. We saw how these defects are the universe's punctuation, the places where meaning is pinned down. But what happens when you have more than one defect? What happens when these singularities do not just exist in isolation, but interact, dance around each other, and become entwined? Today, we move from the alphabet of singularities to the grammar of their relationships. We ascend from simple knots to braids, links, and higher topological structures. This is where topology blossoms from a theory of individual defects into a theory of composite objects. It is where the holophase language learns to form molecules from its atomic letters, creating a vast vocabulary of complex, stable forms. Let us place this in our episode 7 journey. We are still in chapter 5, topological semantics. We began with the digital core, winding numbers, the what. We then located that core in the sigma set, singularities, the where. Now we explore the relationships between these cores, the how they are with one another. This is the natural progression, from identity to location to interaction. Understanding these higher structures is essential for the complete picture, because it shows how the language builds complex, stable entities from simple, singular parts. To get a feel for this, imagine you have two separate loops of string. Each loop is a closed circle, a simple topological object. Now imagine you take these two loops and interlock them, like two links in a chain. You have created a new structure, a link. This is no longer just two loops placed side by side. It is a specific relationship between loops. You cannot pull them apart without cutting one of them. The relationship itself is a topological invariant. Now take several strings, fix their ends at the top and bottom, and weave them over and under each other. You create a braid. The pattern of weaving, which strand goes over which and in what order, is a topological story of how the strands have danced around each other in the space between the anchors. Braids and links are higher-order topological structures. They are to simple winding numbers what a sentence is to a letter, or what a molecule is to an atom. They encode relational information. This defect circled around that one. These two worldlines are intertwined. Those loops are permanently interlocked. In the holophase framework, the worldlines of defects, the paths of singular points through spacetime, can form braids and links. When two vortex lines in a superfluid twist around each other, their spacetime traces form a braid. When a vortex loop is linked with another vortex loop, they form a link in three-dimensional space. These are not just pretty patterns. They are new, stable topological charges at the higher level. They are conserved quantities that constrain the dynamics and give rise to rich, emergent behavior. Linguistically, if a point defect with winding number +1 is a noun, a vortex, then a braid of two such defects is a phrase. Vortex A, circling vortex B. A link of three loops is like a clause describing a bound state. This is the topological grammar coming alive. In the Holophase language, braids and links represent the relational syntax of the topological branch. We already have the digital core, which gives us the nouns, the simple identities, a vortex, a monopole, a charge with a certain winding number. We already have the sigma set, which gives us the punctuation and the locations, the singularities where these nouns live. Now we add braids and links, which act like prepositions, clauses, and sentences, describing how the nouns relate to each other in space and time. Around, through, linked with, braided together. This syntax allows the language to form compound topological objects with properties that are more than the sum of their parts. A linked pair of defects may have different mass, spin, or scattering behavior than two isolated defects far apart. In that sense, it is a new word in the dictionary of reality. In the master tree, this forms a higher subbranch of the topological semantic structure. It is the level where the discrete digital call learns to communicate, to form bonds, and to build complex architectures. Scientifically, we need ways to quantify and classify braids and links. For braids with n strands, the key concept is the braid group. The elements of this group are all possible ways to braid n strands, where two braids are considered the same if you can deform one into the other without cutting strands or passing strands through each other. The fundamental operations are simple crossings, strand I going over strand j at a particular step. The entire complex braid can be described by a sequence of these fundamental crossings, and that sequence is like a word in the language of the braid group. For links, the key simplest invariant is the linking number. For two oriented loops, it counts, with a sign, how many times one loop winds through the other. It is an integer. A simple Hopf link, two interlocked rings, has linking number plus or minus 1. More complex links require more sophisticated invariants, like the Alexander or Jones polynomials, to tell them apart. In physical systems, the worldlines of point defects over time trace out braids in 2 space dimensions plus time, or links in 3 space dimensions plus time. The trajectories of particles in 2 dimensions that exchange positions create braids in their configuration space, and this is the foundation of anyone's statistics in quantum physics, where the phase acquired when two particles are exchanged depends not just on their identities, but on the topology of their braided paths. Vortex lines in 3-dimensional fluids or superfluids can become linked, and this linkage is conserved under smooth fluid flow, a topological constraint closely related to conservation of helicity. All of this lives very naturally inside the holophase picture. The defects are singularities of phi, and the ways those singularities wind around each other are new, higher-level topological data. Braids and links are inherently spatio-temporal concepts. A braid is fundamentally a temporal story. You can treat the vertical direction of a drawn braid as time. The crossing of strands, then, represents one particle or defect passing around another at a specific moment. The entire braid pattern encodes the history of their relative motions. In quantum mechanics, the phase associated with a braid, for example, the statistics of anyons in 2 dimensions, is a direct signature of this temporal entanglement of worldlines. A link, by contrast, is a spatial relationship frozen in time. 2 linked vortex loops in a fluid, or 2 interlocked DNA rings called catenanes, represent a spatial bond that is topologically protected. You cannot separate them by smooth deformation of the space they inhabit. They form a composite object whose connectivity is robust. Motion, in turn, can change braiding and linking, but only in specific quantized ways. To change the linking number of 2 loops, one loop must in effect be cut and pass through the other, a singular surgical event in the dynamics. Smooth motion preserves these invariants. Therefore, the motion of defects is constrained by their topological relationships. They can dance and move, but they cannot simply forget who they are linked to or how they are braided, unless a true topological surgery takes place. These higher structures provide a kind of motion memory for systems. The way things have moved around each other in the past is not forgotten. It is encoded in their present topological relationship. In our episode 7 architecture, we are climbing to a higher node within the topological semantics branch. Beneath this level lie the simple defects and the sigma set, the singular skeleton. At this level, we find the rules for combining those defects into stable composites via braiding and linking. From here, the structure feeds upward into future branches concerning identity formation and particle-like behavior. This is where the language demonstrates its power to generate complexity. From a handful of simple defect types and the rules of topology, an infinite variety of composite, stable structures can emerge. These topological relationships impose powerful constraints on all other dynamics. In relation to the mixed tower, the tower of dynamics, the equations of motion must respect topological conservation laws. Two linked vortices cannot simply drift apart as if nothing ties them. Their dynamics are coupled, and the forces between them can depend on their linking number. In two-dimensional quantum systems, braiding statistics impose deep constraints on the possible quantum states of many particle systems, and are at the heart of the fractional quantum Hall effect and proposed topological quantum computers. In relation to wave semantics, the scattering of waves of a linked defect complex will differ from scattering of isolated defects. The topology creates an effective potential, a kind of geometric scattering center. In relation to the digital core, braids and links are higher-order digital information. While a simple defect has an integer charge, such as +1, a braid is described by an element of a non-commutative group, the braid group, and the link may be described by a polynomial invariant. This is richer, more structured digital data than a single number. In relation to future object semantics, these composite topological structures are prime candidates for what we experience as stable particles or quasi-particles. In some field theories, particles like electrons or monopoles can be modeled as topological solitons with specific braiding properties relative to other fields and excitations. In essence, braids and links are the rules of engagement for the topological sector. They dictate how the singularities can play together. The semantic meaning of braids and links is that they are the dimension of relationship and bond. While simple topology gives us this is a thing, higher topology gives us this is with that. It encodes entanglement, worldlines braided together in spacetime, bonding, objects linked together in space, history, the braid pattern recording the story of past motion, and statistics, how identical particles behave when exchanged, dictated by their braiding behavior. This allows the Holophase language to express not just isolated entities, but communities, molecules, bound states, and networks. It provides the grammar for togetherness. As with the simpler topological invariants, braids and links have their own stability, variability, and experimental tests. Braid types and linking numbers are topological invariants under smooth deformation. A Hopf link remains a Hopf link unless you cut and reconnect the loops. A specific braid pattern remains the same as long as you do not let strands pass through one another. This makes these relationships incredibly stable features of a configuration. At the same time, the possibilities are endless. Even with just 3 strands, there are infinitely many distinct braids. The tables of known knots and links grow very large. Nature and mathematics both explore this variety in complex fluids, polymers, and field configurations. The predictions of this branch are spectacularly testable in engineered systems. In liquid crystals, lasers and electric fields can be used to create and manipulate disclination lines, topological defects in the orientation field of rod-like molecules. One can attempt to create 2 linked disclination loops, then measure a force or an optical signature that confirms they are indeed linked, and even intentionally unlink them via a controlled topological surgery and observe the change. In superfluids and Bose-Einstein condensates, one can create multiple vortices and move them with laser traps, effectively braiding them. In two-dimensional systems, one of the great experimental goals is to measure the anionic statistics of emergent quasiparticles by performing braiding operations and detecting the resulting phase. In structured light, holograms, and sophisticated beam shaping techniques allow us to create knotted or linked structures in optical vortex lines or in polarization fields, and to image these structures directly, confirming their topology. A falsification of this sector of the holophase picture would involve a system where defects are clearly present and mobile, but where no conserved braiding or linking invariants can be found, where worldlines seem to pass through each other seamlessly without any singular event, in a way that contradicts the topological protection predicted by a smooth phi-field description. So far, in systems where the assumptions of the theory hold, we see the opposite. Topology is respected. Nature loves knot work. In physics and quantum mechanics, anyons in the fractional quantum Hall effect are emergent excitations whose quantum statistics are described by braids. Exchanging two anyons is like performing a half braid, and doing so changes the quantum state by a phase factor that is neither bosonic nor fermionic, but fractional, a direct physical manifestation of braid group statistics. In turbulent fluids and plasmas, vortex lines can become tangled and knotted. The conservation of helicity, a measure involving linking and twisting of vortex lines, acts as a topological constraint on the flow. Solar plasma filaments often exhibit twisted and braided structures before erupting as solar flares. In optics, beams of light can be engineered with vortex cores tied into knots or with linked polarization singularities. In chemistry, catenines and molecular knots are literal examples of topological links and knots at the molecular scale. Their synthesis often relies on templates that braid or thread molecular components before closing the loops. DNA topology is an even more dramatic playground. DNA is a long, flexible polymer that readily becomes supercoiled, knotted, and linked. Enzymes such as topoisomerases and recombinases perform precise topological surgeries, cutting, passing strands through one another, and resealing to manage this knotting. Without these enzymes, the cell could not properly replicate or transcribe its genetic material. In biology, more broadly, some proteins fold into knotted topologies. This knotting can stabilize the protein and affect its function. The folding pathway, the process by which the protein achieves its final shape, must in effect tie the knot in the polypeptide chain, a kind of physical braiding in 3 dimensions. In bacteria, plasmids are small, circular DNA molecules. If two plasmids become linked or catenated, they cannot easily separate during cell division. Again, specialized enzymes exist to unlink them, operating directly at this topological level. On cosmic scales, if cosmic streams exist, they would form a network of long, moving strings in the early universe. These strings can intersect, exchange partners, and reconnect, creating an evolving web of linked and knotted structures on a cosmological scale. The cascades of reconnections and the topology of such a network would play a role in the history of the universe's structure and radiation. The logic of braiding and linking also shows up in human and abstract life. In consciousness and mind, memories are not stored in isolation. A memory of a person is linked to memories of places, sounds, smells, and emotions. A traumatic memory can become knotted with fear responses. Learning often means braiding new information into existing knowledge strands, creating a stronger, more interconnected understanding. In narrative and art, a complex novel or film often uses a braided narrative structure, interweaving multiple storylines or timelines. The meaning emerges from how these strands cross and interact, not just from each strand alone. In history and society, civilizations are not isolated blocks. They are linked through trade, migration, conflict, and cultural exchange. The Silk Road was a historical braid of cultures and economies stretching across continents. A modern supply chain is a complex economic braid spanning dozens of countries, vulnerable where strands cross or bundle too tightly. The history of a region is often a braid of different peoples, languages, and technologies moving around and through each other over centuries. The history of science itself is a braid of ideas from different disciplines, crossing and fertilizing each other. In economics and systems, the global financial system is a vast, intricate network of links: loans, derivatives, ownership structures, and obligations. The 2008 financial crisis was a dramatic demonstration of how linkage can transmit failure. The topological connectivity itself became a source of systemic risk. A supply chain for something as simple as a smartphone involves materials whose extraction, processing, assembly, and distribution are braided across the planet. Disruptions, such as a blocked canal or a factory shutdown, reveal just how structured and delicate that braid is. In knowledge and language, the most powerful new ideas often come from braiding together concepts from different fields, such as combining biology with computer science to create bioinformatics, or physics with economics to build econophysics. This intellectual braiding creates a stronger, more flexible structure of understanding. Words themselves have histories that link languages across time and space. English, for example, is a dense knot of Germanic, Latin, French, and many other strands. You can now begin to see the woven and interlocked patterns of braids and links in the world around you. Look at a complex highway interchange. A multi-level stack of roads is a spatial braid of pathways designed to let flows of cars cross without stopping. Trace the path of one road as it weaves over and under the others. Look at woven fabric or a basket. The warp and weft of cloth, the strands of a wicker basket, are physical braids, weaves, and links. The strength and pattern of the material come from the crossings, not just from the strands themselves. If you analyze a family tree or an organizational chart, the lines connecting individuals or departments are links. When lines cross due to marriages, collaborations, or cross-functional teams, a kind of relational braiding appears that defines the network's complexity and resilience. In music, listen to a fugue or polyphonic piece. Multiple melodic lines braid together, weaving in and out, crossing and supporting each other. The beauty lies in the counterpoint, the topological relation of the voices in time. A simple practice is to take two long pieces of string or two headphone cables and lay them parallel. Slowly twist them around each other, creating a simple two-strand braid. Notice how the act of braiding binds them together, creating a single composite cord that is stronger and behaves as one. You have just performed the physical operation that creates a higher topological structure. Now imagine each string as the worldline of a particle moving through time. Their braiding is then a story of how those particles have moved around one another. You are learning that relationships have shape, and that shape has consequences. The universe is not just a collection of things. It is a tapestry of braided and linked stories. And so we return to the one field, seeing it now as a master weaver. These braids and links, these higher topological structures, are still just configurations of phi's singularities. They are specific, stable ways that the sigma set, the skeleton, can be arranged in spacetime. The fact that phi is a smooth, cyclic field forces these arrangements to be countable, classifiable, and persistent. With this, our understanding of the topological semantics branch is nearly complete. We have the digital core, the countable charges. We have the sigma set, the singular anchors, and we now have the braids and links, the relational grammar between anchors. This trilogy explains how the smooth field phi can give rise to a world of complex, stable, relational entities. It is a cornerstone of the complete Holophase language picture we are building in episode 7. As we conclude our exploration of braids and links, hold this image of a woven universe. We have discovered that the singular points in the field are not lonely. They dance, they intertwine. They form bonds that are as real and stable as the defects themselves. From these dances and bonds, the complexity of the world is woven. This higher topology is the universe's art of connection. It is why particles can form atoms, why atoms form molecules, why ideas combine into theories, and why people form societies. It is the grammar of width. In our next part, we will take a final synthesizing look at this topological layer. We will explore part 24, dimensional identity of topological meaning, and see how these discrete relational structures fully express themselves through time, space, and motion, completing the triunity for the topological branch. But for now, see yourself as part of this tapestry. Your life is a worldline, braiding with the worldlines of others, loved ones, strangers, ideas. Your memories and beliefs are linked in a vast internal network. You are not an isolated noun. You are a verb braided into the sentence of existence, a link in the chain of life, a unique and stable pattern in the holophase field. You are a knot of meaning in the flowing cloth of phi. Peace be upon you until part 24.